In this last video, I wanted to talk about how restricting the sample space can actually make such probability questions simpler. Because one of the issues is that like in larger scale problems, the issue is we have 7,000 outcomes and it can be very difficult to list the entire sample space. Even the event space, right, had 32 methods, and the method of brute force might just be too hard to solve. So we might need to rely on a lot of these shortcut techniques to be able to solve them. So let's look at, and the point here is that restricting the sample space can be helpful. So example 12 says an ordinary deck consists of 52 unique cards where 4 cards of each type, ace, king, queen, jack, and 2 through 10. So again, talking about a standard playing card deck. It says, what is the probability that in Texas Hold'em, which is 2-card hand, the player draws an ace and a king, assuming suit doesn't matter. So these sorts of questions are very important to gamblers because there's certain hands that are considered to be very strong and hard to beat. And knowing what the chance of drawing these can be helpful. And let's just say we want to know what's the possibility of drawing ace king and how do I do that. And also I wanted to mention there's a mistake that a lot of people make in these probability calculations, and just as a warning about how to be careful, and again, it kind of circles back to the idea of combinations. But one way we could do this is by restricting the sample space to what are all our possible hands. And if we think about how many total possible hands were there in Texas Hold'em, this was something we did in the previous slide. Remember that there were 1,326 unique hands, and we use combinations to do that because ace king and king ace of different suits are considered the same hand, and it cut down on half of them really at the end of the day. But basically, we've already figured out the number of outcomes in a previous video. The outcomes is equal to 52 choose 2. Again, and it's combinations here because we're not replacing the card, and order does not matter. And that was, well, again, we could redo the math. 52 factorial divided by 2 factorial times 50 factorial, which ended up being 52 times 51 over 2, or 52 times 1 divided by 2 was 1,326. So basically, we know our sample space size. So the probability of our success should be a number divided by that. Because, right, that's the general rule of thumb here, is the probability of an event occurring is the probability of the number of events of that outcome divided by the sample space size. So the sample space, the size of the sample space is super helpful because that gives me the denominator of my fraction. Then all I need to know is my numerator. And so next we want to know, well, how many different ways are there to do ace king? So that's a much simpler question. And then we would take that number divided by the total. So basically, the fact that there's 4 suits of each is like, if I was thinking about hands like ace of spades, I'll just write that as AS, and then king of spades. That would be one potential outcome. I could have ace of spades, king of diamonds, ace of spades, king of hearts, ace of spades, king of clubs. And similarly, basically that would be each hand with aces suited. I could also have an ace of clubs with each, right? I could have an ace of hearts with each, and I could have an ace of diamonds with each pair of kings as well. And none of those are duplicated. So what that gives me is a total of 16 potential hands. Or really, again, I could think about that as fundamental counting principle. In the first card that I draw, if it was going to be an ace, there's 4 ways to draw an ace, and then there's 4 ways to draw a king. And I've already kind of compensated for the error ahead of time in doing that. Or really, I have 4 squared, because each is a different card. I'm like, as I draw the first ace, I'm ignoring the possibility of getting a second ace because it's a unique outcome of cards in there. So basically, the number of events in my event space is 16. So that's number of E. and then the number of total outcomes is that. And then basically my total probability here would be 16 divided by 1,326, which would be the probability of getting an ace or a king, which is approximately 0.0121, or let's just say 0.7, which is approximately 1.21%. So a little over 1 in 100 times you will be getting an ace king is our conclusion here. And another interesting thing is if a lot of times these questions people have asked and answered before if you just Google it, but I remind you to be very careful about trusting the answers you see on internet sites, because a lot of times people who are answering these questions, they might not be math experts, or they might make mistakes and overlook something. So that's why what I wanted to show you in this case. And I did a Google search just to see, and actually one of the very first answers I came up with was actually wrong, and I thought it was quite interesting. But this person asked, what's the probability on one of those internet ask sites? What's the probability of picking an ace and a king from a 52 card deck? So this person finds the number of cards, the number of aces, the number of kings. So they think about, kind of like I did in the last example, what's the probability of my first pull being an ace? So they say that's 4 out of 52. Yeah, of course, because there's 4 aces out of 52 cards. Now the probability of drawing a king is 4 out of 51. Also true. So what they do is they multiply those together, as I said in the last video, which gives me a result of 0.6%. And there's some people have upvoted it. You'll notice that I actually downvoted it because they forgot one very important fact in their calculation here, is that what they just calculated was the probability of drawing an ace, then a king. But technically, you could draw a king, then an ace. That's different outcome technically, even though it's the same hand. So they forgot about the logic of combinations, and that's why their answer is incorrect. And notice that the next person corrects them. Someone commented and corrected them, which let me go ahead and make that bigger so you can probably read it. And they did not get any upvotes, of course, which shows you the power of wrongness on the internet. But Dewey said, there are 2 separate events you forgot to include when first drawing a king and second drawing an ace. It would be the same, so I think that all you have to do is double the final probability, which, yes, that's exactly true, because if you double his answer, 0.00603, what you would get is 1.21%, which is the correct answer. So anyways, it's something that's very easy to do with calculating things is, well, does the order matter? They forgot to multiply by the number of combinations by 2. And that's something that's very key in the binomial theorem or the binomial formula, which basically you would take those odds and you have to multiply by the number of orders, basically by NCR. And when I wrote that formula in last thing, you just take those probabilities, multiply by the number of combinations, which is just 2 because there's only 2 objects being considered. But it's another factor in those more complex formulas. Anyways, wrapping this chapter up, we've gotten really complicated here, and my goal is to not, like, a lot of people really hate or don't like probability because it gets so complicated. But what I'd remind you to focus on are really the basics, which are, you can always figure them out via attrition. And I think there's a little bit of comfort in that. Like, if I really wanted to know all of the outcomes, I could actually find them out. And the basic nature of probability is quite simple, right? Assuming equal probable, assuming that is not a stacked deck, we're going to have a certain number of outcomes and a certain number of acceptable choices, and it's just a simple ratio of the two, right? How many are acceptable outcomes divided by how many total possibilities you have. There are alternative ways to figure them out, but anyways, that will wrap up this chapter. Hope you all are well. I'll talk more about the final a little bit later, but it is cumulative. It will have a little bit of probability, a little bit of chapter 6 and 7 as well. See you all. Bye.